Hello, everybody. This is the solution for how to find out the Jordan form. That's for the course at University of New South Wales. Course is MATH2099, linear algebra. So in this example, we have the matrix A, and we would like to find out Jordan canonical form. First, we would like to find out the eigenvalues and their algebraic multiplicities. Then we would like to find out eigenspaces and geometric multiplicities of the geometric multiplicities, as you remember, as you know, is the dimension of those eigenspaces. Okay. So the characteristics is polynomial of A, as we know, and we need to calculate the determinant of A minus lambda. The roots of this polynomial, this will be a polynomial of degree 3. And the roots of this polynomial will give us eigenvalues. So if we calculate this determinant, we will find out lambda plus 5, lambda plus 2 squared. Now, if we have, so we have two eigenvalues. Lambda 1 is equal to minus 5, lambda 2 is equal to minus 2. These are the roots of this polynomial. And as you see, this is the of order 2. So lambda is equal to minus 2 has algebraic multiplicity is 2. So algebraic multiplicity of eigenvalues are the powers in the characteristic polynomial. So this has only power 1. So algebraic multiplicity of the eigenvalue minus 5 is 1. For the eigenvalue minus 2, the power is 2, as we see, the power is 2 here, then algebraic multiplicity is 2. So if we find, I will say it later. I will hold on a second. So this is the algebraic multiplicity in eigenvalues. Let's try to find out the eigenspaces corresponding to those eigenvalues. So if minus 5 eigenspace, so we call them E minus 5, that is the kernel of A plus 5I. So if you put lambda is equal to 5A here, minus 5A here, that will be minus 4 plus 5, so that's 1. Minus 3 plus 5, that's 2. Minus 2 plus 5 is 3. So the diagonals will change, and all the others will remain the same, right? 2, 1, 1, 1, 3, minus 3. So that is the matrix that we obtain, A plus 5I, that's that one. So as we know how to find out the eigenspaces, we find out the reduced row echelon form of this matrix. If you can use a computer aid for it, use MATLAB, Mathematica, Maple, whatever you're working on, that will be perfectly fine. To reduce row echelon form for this one, or just calculate it, it's a simple matrix. It will take a few steps to do it. Anyway, so reduced row echelon form of this matrix is this form. So last row says us that x3 is free. This row says to us that x2 is equal to 0. Or, So the first row is x1 plus x3 is equal to 0. It means x1 is equal to minus x3. That gives us the basis element of this eigenspace is x2 is equal to 0. If you put x1 is equal to 1, x3 is equal to 1, x1 will be minus 1. So minus 1, 0, 1 will be the basis of this eigenspace. I just would like to remind you again, the eigenvectors of the corresponding eigenvalue minus 5 is all multiples of this vector. So this vector is a basis of this eigenspace. Spanning means this all scalar multiples of this vector. So it is an infinite set. There are infinitely many eigenvectors corresponding to the minus 5. But when we're talking about the eigenvector, we refer to the basis of the eigenspace. So this is the general language that we use. Okay, so what is the geometric multiplicity? Geometric multiplicity of this eigenvalue minus 5 will be the dimension of the space. So it is spanned by 1, so the basis has only one vector. It means that the geometric multiplicity is 1. Here we have geometric multiplicity of 5 is 1, and we also know that algebraic multiplicity is 1 from here. So it means perfectly nice, right? This is what we would like to do in general. If this is the case for all eigenvalues, then we will obtain a basis from eigenvectors of that matrix for the whole space. Then we would say the matrix is diagonalizable. Okay, we need to look at the other eigenvalue. Lambda is equal to -2 eigenvalue, right? So, yeah, we don't need to consider the generalized eigenspaces for lambda is equal to 1 because geometric multiplicity and algebraic multiplicity are the same. Okay, for -2 eigenspace, E -2 is the representation, is the notation for us. Kernel of A plus 2i, so only the diagonals will change. And we will obtain this matrix. So you will just put +2, -2 here, right? -2, -4 plus 2, that will be 2. +2 here, -1, +2 here, 0. So that's -2, -1, 0, and all the others are the same. Again, same idea. We would like to find out the reduced row echelon form. Do whatever you like, calculate or use a computer aid to compute that one. Assume that, I mean, this is the reduced row echelon form that you're going to get it. So I haven't done the work that from here to here, right? There's a dot, dot, dot here, which means that you need to do some work here to get the reduced row echelon form. Or use a computer aid. Ask the computer what is reduced row echelon form of this matrix. Okay, we get this reduced row echelon form. What is the solution? So this is the kernel space, right? So the kernel space means that this times the x vector is equal to 0. So the last row is 0, 0, 0 is equal to 0, which means that x3 is equal to 3 because leading coefficient of x2 is 0, right? This is the coefficient of x3. Leading coefficient in the place of x3. This means that not x3 but x2 is x2 is 3 because leading coefficient of x2 is 0. Okay, so this row tells us that x3 is equal to 0. And since there is no leading coefficient, this is a leading coefficient of x1. This is this place for the leading coefficient of x2, but this is 0. This is why we think that x2 is 3. And leading coefficient of x3 is 1. That will give us 0. I'm repeating myself, but I just wanted to emphasize. So the first row implies that x1 is equal to x2. What is the basis for this one? It's just the one vector because we have one free variable. If you put x3 is 0, so this has to be 0. If you put x2 is equal to 1, x1 is equal to 1. So we have 1, 1 for the basis. This is a basis vector for this eigenspace. The dimension of this kernel, dimension of this space is 1 because we have only one vector which span everything. So geometric multiplicity of -2 is just -2, which is the dimension of this space. -2 is equal to 1, which is the dimension of this space. So the geometric multiplicity is 1. This is how we found it here. We also found previously algebraic multiplicity is 2. So they are not the same. It means that we need to talk about the Jordan form, or we need to talk about generalized eigenspaces, because it is, if they equal, we have an eigenspace. We have enough eigenvectors to produce a basis for the whole space, and the matrix would be diagonalizable. But this is the case. In this moment, we will be able to say that the matrix is not diagonalizable. Now, since the geometric multiplicity is 1, there exists a one Jordan block. So you have -2 is the eigenvalue. One Jordan block means This is not in this format. Only one block. 2 by 2 is one block. Since algebraic multiplicity is 2, this is how I think you've seen this in the lectures. This is a Jordan block, 2 by 2 Jordan block. This 2 represents the size of the Jordan block. This represents the ion value. So the Jordan block of 2 with ion value is this, is -2, and 1. If there's a 2 by 2, we put 1 here and ion value is here, which means that these are not separable. This is not, cannot sort of diagonalize that part. Another option for -2, if we had algebraic multiplicity and geometric multiplicity is 2, then we would have this situation here. Then the blocks would be splitted. We could separate the blocks as we've done here. So it's just one block of -2, another one block of -2. We would be able to do it. It means that we would be able to obtain 2 ion vectors, which means that we would be able to find out 2 basis element of this space, ion space. If that is the case, if we find 2 basis vector of this space, we would have this situation. We would be able to separate it. But we couldn't. We found only one basis. That means that we have only one block corresponding to ion value -2. But we have 2 by 2 matrix with one block. How do you write that? Which is -2, 1, 0, -2. That's the case. I hope this helps. This explanation helps. Let's move on. So what we have, what is the Jordan block of this matrix? What we found so far. So we found that ion value -5 with one block. So J1 -5, because algebraic multiplicity is 1 and geometric multiplicity is 1. So it is 1 by 1 matrix, just -5. And we found here one Jordan block. It is a 2 by 2 matrix, but it's a one block because we have only one ion vector. We cannot separate it. So we have -2, -2, 1. All the other places is 0. So we think this is this representation called Jordan blocks of the matrix A. Why it is useful? So I would like to talk about how significant it is, how beautiful it is, how it is so useful for us. Okay, if we have this, then there exists an invertible matrix S such that A is equal to Sj S inverse. Now, next step, I'm going to show you how to find out S and verify this equality. That's the next step that I would like to do. So for ion value lambda, if algebraic multiplicity is different from the geometric multiplicity, then we need to construct a chain of generalized vectors. So in this case, if algebraic multiplicity and geometric multiplicity are different for that ion value, it means that we need to talk about the generalized ion spaces, generalized ion vectors. What I mean by that? For this one, we have a 2 by 2 block, which means that we need to look at the generalized ion space, which is the kernel of A plus A minus lambda I square. So in this case, this is -2. So we need to look at A plus 2 identity square. So this is A plus 2i. This is A plus 2i, just matrix multiplication. This row with this column with the dot product will give us this point, and so on. So this times this will be -2 will be 4, and 2, 6, and plus 3 is 9, which is that one. So this is how you obtain this matrix. It's just a matrix multiplication row with columns row with columns and so on. So this row with this column -2 plus 2, 0. So this is 0 and so on. Please check these multiplications just to get used to that your mind set, how we multiply the matrices. You should be very comfortable with the matrix multiplication. Anyway, the idea is that to find out the basis of the kernel of A plus 2I. So for this, we need to reduce the echelon form of this matrix, which is A plus 2I squared. The reduced row form of this one, it's very easy. Just multiply, just add these two, then you will have 0, 0. Divide this one by 9, then you will have -1 and 0 out everywhere. So you have no leading coefficient for y, you have no leading coefficient for z. So it means that y is free, z is free. From the first row, you have x minus y is equal to 0. It is x is equal to y. So you have two ion vectors corresponding generalized ion space, this one. The span, so this will be the first one. For example, z is free and nothing else, no other coefficients for the z. So 0, 0, 1 is this corresponds to this situation. Since y is free and x depends on y, you put y is equal to 1, then you will have 1, 1 vector. So you have two vectors spanning this ion space, the generalized ion space, corresponding to ion value -2, right? This is a 2 dimensions. Now the next step, so what we have here, right? We have the Jordan block -2, -2 to 1. Just one block, one Jordan block, 2 by 2 matrix. So it is enough to calculate up to here because it is just a 2 by 2 block. We need only one step, right? I will explain what it will be clear what it means in a moment. But since this is 2 by 2, and this will be enough for 2, right? If your Jordan block is k by k, then you need to calculate kernel A minus lambda I to the power k. And we don't need to calculate the other powers on the top. So the next thing to do is we would like to choose a vector in this kernel space, but not in the smaller kernel space. As I explained last week, the kernels are each other's. This is the key idea here. Kernels are one to another. Okay. I explained that one before. Yes, here we are. This is the key idea for these Jordan forms. For any matrix, if you have kernel M, then it is inside the kernel M squared, kernel M cubed, and side. So this space inside the kernel M squared, this span is inside the kernel M cubed for every matrix. So when you are taking the squares of the kernels, then you would still contain each other, right? So that's what I'm trying to say here. So this one here is inside here. So the vectors, this one is vectors are here. So what I'm trying to say is that if you looked at it, so the kernel of A plus 2I is the basis is 1, 1, 0. And kernel of this one, this space is inside this space, as you see. So what the theory says to you, just find a vector in here, but not in here. So for example, 0, 0, 1, it is good to choose already you have. If you have, there's no other point to choose more complicated vectors than the simple ones. It is already there. The simple one is 0, 0, 1 here, and the other one, everything in the space is a multiple of this vector. As long as you're not choosing that one, you're on the right track. This will work. Okay. And so this is a good choice. W001 is a good choice. So that's to that vector. We write this concept. W is inside in this space, but W is not in this space, right? Because this is another, you cannot write this vector as a multiple of this vector. It is not there. So we write this in a simpler form. This is a notation. I'm pretty sure this notation have been introduced to you in many other places, but you may not be aware of it. This notation means that the W is inside here, but not in that space. So we denote with the backslash. So the slash here, this element is inside this space, but not in this space. This is a very common notation. I just would like to remind you, if you see it, don't shortcut. It means that this belongs to here, but this does not belong to here. So it means that this is the part of this space, and W is in that arrow, in that back in between spaces. Okay, let's take the W and then apply to the R from A plus 2I, right? And then we will find a vector V. Let's see what we are going to find it out. If you apply A plus 2I to the W, this is A plus 2I, and this is W for us. And if you calculate, this times this will be 1, this times this one will be 1, this times this will be 0. This is the vector V. And this vector is exactly here. It doesn't mean that it doesn't have to be exactly this vector. It is okay to be a multiple of it. Why we are doing it? It will all make sense soon. Be patient. Okay, what this means? This means that we found A plus 2IW is in V. And we also know that V is in this space, which means that A times V is equal to minus 2 times V, because V is in the kernel. V is the ion vector of minus 2. This is what it means. So this V is an element here, means that AV is equal to minus 2 times V, because V is an ion vector of the ion value minus 2. From this equation, A plus 2IW is equal to V, which is this equation. Now, we have AW and we have 2W. Take the 2W on the right-hand side. Then we will have V minus 2W. So we have two equations. Now, we know that the matrix multiplications works with the block by block. So think about the matrix, which are the columns are V and columns of W. If you're multiplying the matrix A, then that will be A times V, that will be A times W. So A times V, which is this equation. If you multiply, so I'm figuring out, basically I wrote this one, and I wrote this one. So this is the same matrix, like VW is the same matrix. And then I'm figuring out this matrix, this one. So AV is equal to minus 2V, right? Matrix multiplication says that this times this times this. So this is minus 2V. From here, AV. So this is that one. Correct. So this equation, AW, this row with this column, V minus 2W, V minus 2W. This times this gives you this right-hand side, which is AW, which coincides with that. So this equation is satisfied. This equation holds because we have this one and we have this one. So these two equations, if and only if, we have this matrix equation. We have done such calculations before, but this is the case for this block only, because that's we need. We need that kind of idea for this block. this is already an eigenvalue such that algebraic multiplicity and geometric multiplicity are the same. So we don't need to having such ideas for this part. But we need a kind of a chain for this part. Okay, this is what's going on. This is why we need to do this. We need to find this kind of a chain to figure out this kind of equation for this part. And now let's get all this information together and find out this S and S inverse. Remind ourselves that what is the E minus 5 span for? This is this vector. So set S, because we know that the order is very important. When we were working on the diagonalizable matrix, we realized that too. Each time you have the eigenvector corresponding to eigenvalue in the diagonal, that's exactly the same idea. The idea didn't change. So this is the eigenvalue, and this is the eigenvector corresponding that eigenvalue. And these are the eigenvalues corresponding to generalized eigenspaces corresponding to eigenvalues of -2. Okay. Only thing differs in this context is that instead of you think eigenspaces, you are thinking generalized eigenspaces. Okay. So with this idea, this is V, this is W. So this is since we have -5 in this corner, we have the eigenvector, which is the basis of the eigenspace E minus 5 in here. Then claim that A is equal to S, J, S inverse. Now, this theory tells us this is the correct. Now let's try to find out. Let's check it. So you can find that S inverse, you know how to compute the S inverse. You put the S here, you have the identity matrix, and you construct a large augmented matrix. You apply row operations. In the end, on the left-hand side, you find an identity matrix. Your aim is to find out the identity matrix. On the right-hand side, you will find the inverse. Of course, not every matrix are invertible. And a matrix is invertible if and only if the determinant is non-zero. If it is invertible, so this is one way to find out the inverse. Otherwise, it is really not easy work to find out the inverses. And these days, we usually ask the computer to find out the S inverses for us. Just to use MATLAB, Mathematica, or Maple, whatever is you like to use to calculate the inverse of a matrix. We can do this just a checking, since if you are in a position that you will not, you don't calculate the S inverse, or it is difficult, you can do it in a corner. You can check your calculation in a corner such that AS is equal to SJ. If you multiply this equation from the right-hand side with S, then S inverse S will be identity. So there's an S here. So this equality is also AS is equal to SJ, right? This is equivalent to AS SJ, because if you multiply S here, then you will have AS is equal to SJ. So if you multiply AS, for example, A matrix with the S matrix, and then you multiply S and the J matrix, which is a J matrix, you will see that these two matrices are the same. That will be a way to check your calculations are correct. Okay, now I would like to talk a little bit application of this in the ordinary differential equations. And applications of the Jordan forms are enormous. It is very important in mathematics. And one of the key significance of the Jordan forms is that similar matrices have same Jordan forms. And that gives us a conjugation concept in the group theory. And then this gives rise these ideas gives a huge theories on the representation theory, and that gives a huge ideas of the theories and quantum. It goes up to the, we constantly use it. It is so basic and it is so important. The idea is very important. The development was very important. Okay, let's have a look at the applications of the ordinary differential equations, ODEs. Assume that we have such an ordinary differential equation system, y1, y2, y3, and y1 prime, y2 prime, y3 prime. This is derivative of the functions. You have three functions. And we have the initial values are given in that way, and we would like to solve this system. As you realize, the coefficient matrix is A, and the vector y1, y2, y3, and then the right-hand side, we have the derivatives of those functions, and this is the initial vector. So basically, this equation system is equivalent to AY is equal to Y prime, these matrix equations, right? So we would like to solve these equations by using a linear algebra, not by using the calculus method. We would like to use an algebraic method to solve these equations. And from these above equations, we have A is equal to Sj S inverse. J is the Jordan block, Jordan matrix. S is we calculated this, and I just find it out S inverse for you and plug it in here. This times this is identity. You can check all the time. This one and this one is just 1. And this one and this one is 0. This one and this one is 0. This one, 1. This one is 0, and so on. So it's an identity matrix. So this is this S inverse of this one. And from the lectures, we know that how to write down AJT, just the definitions in that moment. So I need to give these definitions, and then it will explain in the end. Just this is just a definition of the exponential. J is the Jordan form, and T is the determinant. Right? T is the variable. Sorry, T is the variable, indeterminate variable. Okay. That is J in our form, Jordan form is J1 minus T minus 5 and J2 minus 2. And I think I forgot the T here. I think that should be T here. And also T here. So this one is just E exponential minus 5t. This is just 1 by 1 block. This one will be J2 2 by 2 block. This is e to the minus 2t, and we have t here. And this is just a formula. So I'm just plugging in this formula. Then the derivations of this formula can be, you can find it in your lecture notes or other books, whatever the reference is. The general structure for this one, for the Jordan block, so TJR lambda is given by this formula. This is the general form. So this is E, if lambda is equal to minus 2, this is minus 2. So E minus 2 here, E minus 2 here, E minus 2 here. This is this situation. And this T corresponds to this one. So this little square is this little square here. This 2 by 2 matrices is this 2 by 2 matrices. If you have 3 by 3, then you need to think about 1 over 2 t squared. Then you have e to the minus 2t, and so on. Right? And these are the ones on the diagonals. 0 is below the diagonal. Just one above diagonal, you have t's. One above that diagonal, you have 1 over 2 t squares, and so on. Each time that you're writing down this, you will have one less thing. So you're taking this one, cut here, place it here, cut there, place it here, and so on. This is how it goes. In the end, you have this one here, and the last one is this one. Whatever the way that you want to learn, but you can observe it as just a formula. This is the formula for the one Jordan block. So this is the one for the Jordan block. And we know that the Jordan blocks are linked to the direct sums with the block by block. And the Jordan matrix form of the matrix is basically consists of the Jordan blocks of the matrix. So that one and that one. Okay, so we have exponential JT, which is that matrix here. This is also given in the lecture. So exponential AT is defined by S exponential JT S inverse. Given that A is equal to SJ S inverse. So this one is already you have. With taking the exponentials, you have this one, this equality. This equality, the solution of such system is given by this equality. So the solution space YT is this matrix times to the initial vector. So this matrix is this matrix, which is S, and we know exponential JT, we've just calculated above, plugged it in, and S inverse, just found it, plugged it in, and this is the initial vector, plugged it in. All we need to do is just calculate this multiplication. This will give us a solution space with the initial values. There was a lot of preparations, I know, for a lot of iterations, but this is amazing. What we found here is amazing. Just multiply those things. This 3 multiplication gives you that one. So this is the matrix. This is a solution. If you can change, this is the initial vector. You can change this initial vector. You can, for any initial vector, you just multiply with this matrix, and that will give you the solution corresponding that initial value. So this is the particular solution, and this is the general solution. This matrix corresponds to general solution. This matrix, equations, this vector corresponds to particular solution. So this is y1t, this is y2t, this is y3t. I would like to just think for a minute, for a few minutes. Even though the calculations are seems complex, but it is very useful to think about such solutions for general forms. If you have a really, really rich matrices for A, and all you need to do, calculate the eigenvalues and generalize eigenspaces and Jordan blocks. And when you calculate the Jordan blocks, you automatically have the solutions for all. So you're not doing particular things one by one. It is like an automated way. It is like a programmable way. Let me put it that way. So we can program the solutions with this way. So this is why it is so amazing. And it is very useful to knowing the Jordan forms, Jordan blocks. This is just one side of it. This is just one application of it. It has a huge applications, especially the key idea is that every matrix has their own, every similar matrices have the same Jordan form. That gives you a classifications of the conjugation. It gives you understanding of the group structures, very important group structures in maths, and it is very useful for the theories in the what world actually. Okay, that's all for this one that I would like to do. Thank you very much for listening, and hopefully it is useful for you.